Good morning, everyone. Now we'll start with the process of breaking the current. So, the process of breaking the current in case of circuit breaker. The figure here shows the state transition diagram of the circuit breaker. It is actually the state transition diagram of the circuit breaker. So, state transition diagram of circuit breaker. The state in which the contacts are open and the state in which the contacts are closed are two steady states of the circuit breaker. That is, in this case, you will see that the state in which the contacts are closed and the contacts are open, these are actually the two steady states of the circuit breaker. Steady states of the circuit breaker, and it can remain in these states for the infinite amount of time provided the voltage across the contacts when open, it will remain in this state for the infinite time provided that voltage across the contacts when open and the current through the contacts while closed is either less than or equal to the rated value. Is either less than or equal to the rated value, and under this condition it will remain in this state only. In case the current shoots beyond the predetermined value, if it is greater than the rated value or the predetermined value, then the circuit breaker is called upon to interrupt the circuit. Now, one another situation is there. Let us suppose that if there is over voltage in the system, let us suppose that there is over voltage in the system. Now, what happened in that very case? So there is not much that the circuit breaker can do. So circuit breaker cannot do anything in that. In case of the over voltages, when the voltage is very high, the surge suppressors or the lightning arrestor, the surge suppressors or lightning arrestors surge suppressors or the lightning arrestor is supposed to kick in and bypass the over voltage to the ground. What they do? They bypass the over voltage to ground. They will bypass the over voltage to ground by providing a short circuit till the excess energy is dissipated. So a short circuit is provided in that it will till the excess energy is dissipated, after which after which the overvoltage protector device is supposed, this overvoltage or the surge suppressor or the lightning arrestor is supposed to automatically shut off and avoid the permanent short circuit. So this happens whenever there is the overvoltage in the system. Now, when you will see, when the circuit breaker is in the open state, there is full line voltage across the contacts. That is, under the open state, there is the full line voltage across the contacts. These are, let us suppose these are two contacts of the circuit breaker, and this is a full line voltage across the contacts, and in that very case the current is equals to 0. So the current through the breaker is 0. Now on the other hand, the situation is exactly opposite. In the closed state, what happens in the closed state when the circuit breaker is closed? In that very case, the voltage is 0 and the current is actually the full current. Voltage is 0 and the current is, in this case, is the full current. So the current in the closed state can have values from no load to short circuit current level. So the current in the closed state have the values from no load to short circuit current level, while the voltage across the contact is 0. So the value of the current, it can be from no load to short circuit, and in this case the value of the voltage is practically 0. So the power dissipated when the breaker is either in the open state or the closed state as shown here is equals to 0. So therefore, even the circuit breaker has a voltage and the current rating. Even the circuit breaker has the voltage and the current rating. So the circuit breaker has the voltage rating and the current rating, but from this it is seen that it is stressed because of only one of them in steady states of being open or being closed. So it is stressed being one of them. It is stressed because of one of them, because of either voltage or current in steady state. That is the state of being closed or the state of being open. Now, let us discuss the detailed circuit breaker operation from the instant the trip coil is energized until the successful operation of circuit breaker with the help of the figures. Now it shows the basic flow chart of circuit breaker working. Now, however, one thing must be taken into consideration. Now we have assumed in this case that power factor of current is quite low, so to give a high restriking voltage. So the power factor in this case is quite low to give a high restriking voltage that we will discuss. Now, now the circuit breaker starts from the point at which the trip coil is energized. That is, first of all, fault takes place, then CT and PT is there, then the relay operation. Now this is here the circuit breaker starts. So it starts at the instant when the trip coil is energized, and after a brief delay, which is a function of time constant of the coil and the moment of inertia of the mechanism. So after the brief delay, which is a function of time constant of the coil and what's other thing? Moment of inertia of the mechanism. So the contacts start separating. That is, when the trip coil is energized, after a delay, which is a function of time constant of the coil and the moment of inertia of the mechanism, the contacts start separating. Now, the current at the instant of contact separation will in all possibility be not zero. So, when the contacts start separating, the current will not be zero. So, as soon as the contacts separate, an arc is struck. An arc is struck, allowing the current to flow till its natural current zero. So, arc quenching goes on till the natural current zero is there. Now, during this arcing period, if you see that during this arcing period, what happens during this arcing period? Voltage across the arc is small. Voltage across the arc is small, but as soon as the arc extinguishes and tries to recover from arcing, the voltage appears across the contacts of the circuit breaker. So, during this arcing period, the voltage across the arc is small, but as soon as arc extinguishes and tries to recover from the arcing, the voltage appears across the contacts of the circuit breaker. Circuit breaker. However, this recovery voltage, this is known as the voltage which appears across the contacts of the circuit breaker. It is known as the recovery voltage. This voltage is known as the recovery voltage. And this recovery voltage is actually the function of power factor of fault current. Power factor of fault current as well as the system inductance and the capacitance. Now, as well as system inductance and capacitance, and it so happens that the natural current of resulting transient, it so happens that the natural frequency of the resulting transient, this recovery voltage or the transient voltage, this natural frequency of resulting transient, it is much higher. It is much higher than the power frequency. Much higher than power frequency. Let us suppose we represent it as P frequency. And because of high frequency of transient voltage, because of this high frequency of the transient voltage, that is the high frequency of the transient voltage, the circuit breaker is subjected to very high rate of rise of voltage. Circuit breaker is subjected to very high rate of rise of voltage. So we have the recovery voltage, which is actually the function of the power factor and the fault current system, power factor of the fault current and system inductance and capacitance. And this natural frequency of this resulting transient voltage, it is very high, higher than the power frequency. And because of this higher frequency, circuit breaker is actually subjected to a very high rate of rise of the voltage. And this voltage has a tendency to cause the arc to reignite. And this voltage, high rate of rise of the voltage, let it be dy by dt. So what it does, it has the tendency to reignite. It has the tendency to cause the arc to reignite or restrike. And it is called the restriking voltage. The restriking voltage. So this is how the restriking voltage is there. Now, the transient recovery voltage, we can say that it is the voltage, it refers to the voltage that appears across the breaker contacts. Now, the transient recovery voltage refers, what is the transient recovery voltage? So it is actually the voltage which appears across the breaker contacts immediately after the extension of the arc. Immediately after the extension of the arc. And steady state recovery voltage. Steady state recovery voltage. What is that voltage? Is the voltage across the breaker contacts in steady state when open. That is the voltage across breaker contacts during steady state. That is when open. Now the arc will keep on restriking this arc. It will actually keep on restriking after the first few current zero, because the breaker will need some time to fully organize its arc extension mechanism. So arc will keep on restriking. It will keep on restriking after a first few current zeros. After the first few current zeros, because the breaker will need some time to fully organize its arc extension mechanism. So breaker will need to organize its arc extension mechanism. Arc extension mechanism. Now, subsequently, the breaker will be able to prevent further restrikes and finally recover from the arcing phenomena. Now, whatever we have discussed, it is under the assumption that what the assumption we have assumed? We have assumed that the current at the instant of contact separation is not zero. Current at the instant of contact separation is not zero. Now the question arises, what if the current at the precise instant of the contact separation is zero? So what happens when the current is equals to zero at the instant of contact separation? At the instant of the contact separation. Now in that case, the breaker will be saved from arcing. Now what will happen under this scenario? The breaker, there is no arcing. The breaker will be saved from arcing, and the success of circuit interruption will depend upon the ability of the contact gap to withstand the transient restriking voltage. So there is no arcing because current is zero at that very time, and the breaker is saved from that, and the success of the circuit interruption will depend upon the ability of the contact gap to withstand the transient restriking voltage. It is theoretically possible to design a circuit breaker which always manages to part its contact at the precise instant of the current zero. Such a device is actually known as such a device is described as a synchronous circuit breaker. Now, what is the synchronous circuit breaker? That is the circuit breaker which manages to part its contacts at the precise instant of current zero. So we can call it as a synchronous circuit breaker. And however, it is practically very difficult to design a synchronous circuit breaker because of the large, you can say, the rate of change of energies involved. So large rate of change of energies which are involved in that, which are required to move the contact system. So synchronous circuit breaker, it have not met much success now, up till now. How research is going in that very case. Now we will discuss the arc. What is arc? Now before going to that, whatever we have discussed, that is, we will start, the trip coil is energized, then contact starts separating, then the arc is struck, then arc quenching goes on, natural current 0 is there. If yes, then the arc get extinguished, transient restriking voltage appears across the contacts that we have discussed. Arc restrikes. If it is yes, then again process is followed. If it is no, then interruption successful and circuit breaker successfully open the circuit and it is stopped. Now this is explained with the help of this waveform. Now from this waveform you will see that when the trip coil is energized, we will have this circuit current through the circuit breaker and the voltage across the circuit breaker. Now under the trip coil is energized, that is, trip coil is energized at that particular point of time. Contact starts separating. At 2, the contact starts separating. Now first natural current 0 is there in this case because we have to quench the arc and it is related to the current. So the first natural current 0 is there at this particular point, and the arc get extinguishes, but it restrikes as we have discussed because there is the voltage across this voltage is there, rate of change of voltage is there, so it restrikes. Now 4, it is again, we will have the second natural current 0 is there at 4, and arc again extinguishes and the voltage across that is this one, so it again we will have it again restrikes. Now the third natural current is 0 is there, then the arc get extinguished and does not restrike again. And here we will have the magnified view of the around that instant 3, that this one, what is the voltage across that, and then this instant, then we will have the instant 3, then we will have the restriking voltage, transients are there 3 and 4, and then we have the restriking voltage 5 is there in that very case also. So it is shown with the help of the waveform. Now we will discuss that the arc. Now when the contacts separate, the current does not fall to 0. Why it does not fall to 0? When the contacts separate, if you see, when the contacts separate, the current in this case does not fall to 0, and this is due to the fact that, what is the reason behind that? The inductance of the system does not allow the current, inductance of the system does not allow the current to go to 0. Now the current thus continues to flow its pre-separation waveform, and so this current, this continues to flow its pre-separation waveform, and is forced to flow through smaller and smaller contact areas. areas, giving rise to the liberation of the heat. So heat is there. So due to the surface irregularity, one more point, due to the surface irregularity, small area remains in contact. The area which remains in contact is very small. Contact area is small, giving rise to, since the contact area is small, then it will give rise to high resistance through which the current is forced to flow. So since the area is small, so if the area is small, then in that very case the resistance is high through which the current will flow. So the resistance is high through which the current is forced to flow, and this causes the intense heat liberation This causes the intense heat liberation. This causes the intense heat liberation at the point of the contact. At the point of the contact, what it causes because of the heat? It causes the vaporization of the contact material. Vaporization of contact material due to heat. And making the establishment of arc easier as the contacts finally part. So what is this arc? This arc actually consists of ions disassociated from the gas molecules, even you can say that in the oil circuit breaker, oil is decomposed into hydrogen gas, which is an excellent interruption medium. So these are ions disassociated from the gas molecules because of the high temperature and high energy. Due to the high temperature and high energy. Now, what is the physical state of these ions? The physical state of the arc is actually not ions. The physical state of the arc is known as the plasma. The physical state of the arc is known as plasma. It is known as the plasma, and plasma is actually known as the fourth state of the matter, the other three being solid, liquid, and gas. It is known as the fourth state of matter, the other being the solid, liquid, and the gas, and typical temperature within the plasma is of the order of 5000 Kelvin. And the conductivity of this plasma, if you see, conductivity of this plasma is 13 orders of magnitude more than the air. greater than here, and however it approaches the conductivity of the carbon. Now, this tremendous range from excellent insulator to efficient conductor cannot be reproduced by the matter in any other form. So this range from excellent insulator to efficient conductor cannot be reproduced by matter in any other form. So the plasma is the most effective switching medium known. So because it has the tremendous range from the excellent insulator to the efficient conductor, which cannot reproduce by the matter in any other form. So plasma is the most effective switching medium known. So most effective switching medium. Which is due to the fact that its range from excellent insulator to the efficient conductor cannot be reproduced by matter in any other form. Now, once the arc has been initiated by the separation of contacts in a circuit breaker, the high temperature needed to sustain the arc is provided by the current passing through the arc. So, once the arc has been initiated by the separation of the contacts in the circuit breaker, the high temperature which is needed to sustain the arc is provided by the current which is flowing through the arc. Now, one more point: when the current passes through the natural current zero, in that very case, it can no longer sustain the arc and hence the circuit is broken. So, irrespective of the point on the current wave at which the breaker attempts to interrupt the current always get interrupted at the natural current zero. So, what point we get? We get the irrespective of the point on the current wave at which the breaker attempts to interrupt, the current always interrupted at the natural current zero. The circuit breaker is so designed that contacts regain their dielectric strength as quickly as possible after the current zero so that the arc does not get struck. So, breaker is so designed that contacts regain their dielectric strength as early or as quickly as possible after the current zero, so the arc does not restruck. So, however, this may not be possible at a very first current zero after the contact separation, as we have discussed in the graphs also. However, in a high-speed circuit breaker, at least 2 or 3 in high-speed circuit breakers at least 2 or 3 cycles of cycle of the power frequency elapse before the contact gap successfully withstands the restriking voltage for a high-speed circuit breaker. Now, as long as voltages are low, in that very case, the arc is prevented from reignition by the sheath of positive ions that appear at the negatively charged contact within a microsecond after the recovery voltage rises. So as long as the voltage are low, the arc is prevented from the reignition by a sheath of positive ions that appear at negatively charged contact within the microsecond after the recovery voltage rises. The sheath is able to withstand a few hundred volt depending upon the contact material and the surface condition. Now, double break or multiple break devices can exploit this effect even at higher voltages. In a circuit breakers which are designed to operate at thousands of the volts in kVs, the circuit breaker which are designed for thousands of the volts means must be provided for cooling the arc column to prevent the reignition. So means must be provided for cooling the arc column to prevent the reignition. To prevent the reignition. Cooling the arc is actually not easy as one can imagine. If one tries to hasten the heat loss either by using more effective cooling gas or by forced convection, the arc temperature does not decrease but increases. So if we are using the forced convection for cooling purposes, for cooling that, then the temperature might increase. So this is counterproductive behavior and can be understood if one keeps in mind that the outer zone of the arc do not respond to the forced cooling. That is, the outer zone of the arc do respond when we are providing the cooling. Outer zone of the arc respond to the forced cooling and lose their conductivity. Respond to forced cooling and their conductivity is lost. And their conductivity is lost, causing a reduction in the cross section. When the conductivity is lost, it causes the reduction in the cross section area of the arc, and the current density in the arc increases. Now when we have this will increase. However, the current density as a whole, if you see, current density will increased in the arc. Current density in the arc will increase, and which increases the heat liberation. Heat liberation will also be increased in that very case. So we can say that the forced cooling is effectively used in the high voltage circuit breaker. So forced cooling cannot be used in high forced cooling cannot be used effectively in high voltage circuit breakers. Now, however, if you see that there is the necessity of the arc is required. So what is the necessity of this arc? what is the necessity of the arc? Now, from this discussion that we have discussed, that the arc should not create the impression that the arc is something which is undesirable. However, if you see, the arc is very essential part of process of breaking the circuit. So it is an essential part of process of the breaking the circuit. If the no arc is there, that the current would have been abruptly. If the arc is not there, then current would be abruptly forced to zero. And after the contact separation, so when the current is forced abruptly to zero after the contact separation, then it causes the severe over voltages. It causes the severe over voltages and damaging the breaker itself as well as other components of the power system. So, damages the breaker and other components of power system. So, sudden collapse of the current to zero and the over voltage is very similar to the phenomena of the water hammer. That is, it is having the analogy with the water hammer. That is, in hydraulics, if you see, is when we a sudden valve closure in a water pipe full of flowing water. So when the water is flowing and we are closing, suddenly we are closing the valve. In that very case, what happens? The flowing water, it gives rise to build up of high pressure. Pressure will increase in that very case. So when we are using the valve when it is water is flowing in a pipe. So now if the current is abruptly brought to zero, let us suppose that current is abruptly brought to zero from a value I chop. So current is abruptly brought to zero, and let the current be I chop. Then the energy stored in the system inductance in the form of the magnetic field. So energy stored in system inductance in the form of magnetic field. So it is 1 by 2 Li chop square. So this is the energy stored in the system inductance in the form of the magnetic field. However, it is transformed into the system capacitance in the form of stored energy transformed into the system capacitance in the form of stored energy and what's the value? 1 by 2 Cv square. Now 1 by 2 we'll have 1 by 2 L I chop square equals to 1 by 2 CV square. So the voltage now can be expressed as V equals to L divided by C into I chop. Now, in this case, if you see that the capacitance C in this case is stray capacitance of the electrical system, which is quite low. Stray capacitance, and the value is quite low, and in order to accommodate the stored energy of the system inductance, this capacitance is quite low. So to accommodate the stored energy of the system inductance, the small capacitor has to be charged to a very high voltage. It means that the voltage should be increased. That is, to accommodate the stored energy of the system inductance, stored energy of the system inductance, the small capacitor has to be charged a very high voltage. Which is obvious from these expressions. Now, what the arc do? The arc delays the interruption of the current up to the natural current 0. So what the arc do? Arc delays the interruption of the current till natural current 0. So the energy stored in the system inductance is 0, and hence the interruption does not. So it delays the interruption till the natural current 0, and the energy stored in the inductance which is equals to 1 by 2 Li chop square. So this is 0. Then energy stored in the inductance is 0 and does not cause any high voltage as a result of reappearance of energy stored in the inductor, and does not cause the high voltage as a result of reappearance of energy stored in the inductor. So we can say that while we should definitely aim to break the circuit quickly, however, it should not be done too quickly. So what we can do, we aim to break the circuit quickly. However, it should not be done so this is how the arc helps in the breaking the circuit. Thank you very much for this lecture.